Good day, students. How are you doing so far? I hope you're doing very well. This is your physics teacher, Sir Glenmark A, and we are now on the fifth module of General Physics 2 in Quarter 4, which is about relativity. Today, we will discuss our first lesson on special theory of relativity, which is the postulates of relativity. The objective of our lesson today is, at the end of the lesson, the students should be able to state the postulates of special relativity and their consequences. This topic is the introductory topic of the special theory of relativity. We will be integrating the concepts that we will learn here on the lesson about relativistic time, length, speed, and momentum. Before we go on with the lesson, I will first give you a 5-item pre-test to let me know about your previous knowledge of the topic. Get a piece of paper and a pen. For multiple choice questions, write only the letter of your choice, while for the true or false questions, write the word true if your answer is true, or write the word false if your answer is false. I will give you 5 seconds to answer each question. Are you ready? Okay, here is our first question. Who formulated the special theory of relativity? Again, who formulated the special theory of relativity? A. Albert Einstein, B. Isaac Newton, C. Michael Faraday, or D. Arthur Compton? Your time starts now. Time is up. The correct answer is A. Albert Einstein. Question number 2. Who were the two American scientists who tried to experimentally detect the existence of ether? Again, who were the two American scientists who tried to experimentally detect the existence of ether? A. Michelson and Newton, B. Michelson and Einstein, C. Michelson and Morley, or D. Michelson and Graham? Your time starts now. Time is up. The correct answer is C. Michelson and Morley. Question number 3. Which of the following is not a postulate of special theory of relativity? Again, which of the following is not a postulate of the special theory of relativity? A. Relativity postulate, B. Speed of light postulate, or C. Energy postulate? Your time starts now. Time is up. The correct answer is C. Energy postulate. Question number 4. True or false? When an object moves at a much greater speed which is closer to the speed of light, its mass increases. Again, true or false? When an object moves at a much greater speed which is closer to the speed of light, its mass increases. Your time starts now. Time is up. The correct answer is true. Question number 5. True or false? When an object moves at a much greater speed, which is closer to the speed of light, its length parallel to its direction of motion will be observed to be shorter. Again, true or false? When an object moves at a much greater speed, which is closer to the speed of light, its length parallel to its direction of motion will be observed to be shorter. Your time starts now. Time is up. The correct answer is true. So, did you get all the 5 questions correctly? If you did, that's great. If you didn't, don't fret because you can still get it in the next test. So, get yourselves ready and listen attentively to the discussion. Let's begin. When the year 1905 began, Albert Einstein was an unknown 25-year-old clerk in the Swiss Patent Office. By the end of that amazing year, he had published several papers of extraordinary importance. The first paper that he published was about the photoelectric effect, which was entitled On a Heuristic Point of View Concerning the Production and Transformation of Light. This was published on March 1905. In this paper, Einstein proposed that light is composed of tiny particles called quanta. Consequently, the paper led to the development of the branch of physics known as quantum mechanics. The second paper that he published in that year was his doctoral dissertation, which was completed on April 30, 1905. The paper was entitled The Determination of Molecular Dimensions. This was submitted to the University of Zurich on July 20, 1905. A somewhat different version was submitted to Annalen der Physik on August 19, 1905 and published in 1906. The third book that he published was an analysis of Brownian motion. This was published in May of 1905. This has a title of On the Movement of Small Particles Suspended in Stationary Liquids Required by the Molecular Kinetic Theory of Heat. This was published in Annalen der Physik or the Annals of Physics. The fourth paper that he published that year was entitled On the Electrodynamics of Moving Bodies, which is about the special theory of relativity, which was published on June of 1905. This paper proposed drastic revisions in the Newtonian concepts of space and time. The fifth paper that he published in that year was a supplement to the June 1905 Special Relativity paper. It has a title, Does the Inertia of a Body Depend upon its Energy Content? This was published in September 1905 and was found on Annalen der Physik or the Annals of Physics. The special theory of relativity has made wide-ranging changes in our understanding of nature, but Einstein based it in just 2 simple postulates. One states that the laws of physics are the same in all inertial frames of reference. The other states that the speed of light in vacuum is the same in all inertial frames of reference. These innocent-sounding propositions have far-reaching implications. Here are the 3 implications. First implication states that events that are simultaneous for one observer may not be simultaneous for another. The second states that when 2 observers moving relative to each other measure a time interval or length, they may not get the same results. Third, for the conservation principles for momentum and energy to be valid in all inertial systems, Newton's second law and the equations for momentum and kinetic energy have to be revised. Relativity has important consequences in all areas of physics, including electromagnetism, atomic and nuclear physics, and high-energy physics. We will discuss thoroughly these implications when we discuss the two postulates of Einstein. Einstein's first postulate, which is called the principle of relativity, states that the laws of physics are the same in every inertial frames of reference. If the laws differed, that difference could distinguish one inertial frame from the others, or make one frame somehow more correct than the other. Here is an example. Suppose you watch two children playing catch with a ball while the three of you are aboard a moving train with constant velocity. Your observations of the motion of the ball, no matter how carefully done, can tell you how fast or whether the train is moving. This is because Newton's laws of motion are the same in every inertial frame. Another example is, if you are in a bus moving with constant velocity and you throw a ball up, it will simply fall down on your lap in free-fall motion. But an observer outside the bus, say on the street across the moving bus, will observe the ball as a projectile which was thrown at an angle from the horizontal. During the 19th century, most physicists believed that light traveled through a hypothetical medium called the ether. The ether is defined as a hypothetical medium which pervades the universe in which light waves were supposed to travel, just as sound waves travel through air. If so, the speed of light measured by observers would depend on their motion relative to the ether, and would therefore be different in different directions. The Michelson-Morley experiment, which uses light beams and half-silvered mirror, was an effort to detect motion of the Earth relative to the ether. The results of the experiment show that no matter which direction the beams of light were aimed, they always bounce back at exactly the same instant. Therefore, there is no ether at all, and so there is no such thing as absolute motion relative to the ether. The result also shows that the speed of light is the same for all observers, which is not true of waves such as sound waves and water waves that need a material medium in which to occur. The result of the Michelson-Morley experiment proved Einstein's second postulate, which states that the speed of light in vacuum is the same in all inertial frames of reference and is independent of the motion of the source. This postulate implies that it is impossible for an inertial observer to travel at c, which is the speed of light in vacuum. To illustrate this statement, consider a rocket which is launched from a space station. Light is emitted from the station at 300,000 kilometers per second, or equivalent to the speed of light in vacuum. Regardless of the velocity of the rocket, an observer in the rocket sees the flash of light passes her at a speed of c. If a flash is sent to the station from the rocket, observers in the station will measure the same speed of light to be c also. Thus, it could be inferred that all observers who measure the velocity of light will find it to have the same value, which is equal to c. When you look at the stars, you are actually looking backward in time. The farthest stars that you see in the sky are actually the stars that you may have seen long ago. Using the two postulates, Einstein was able to prove mathematically that Newtonian laws are for objects at rest or moving at very low speeds. But when speeds involved are comparable to that of light, as in the case of atomic particles, there are corresponding changes in the physical properties. Okay, students, we are done with lesson 1 of module 5, which is about the Einstein's postulates of relativity. I hope you have learned many things in our discussion today. If you have clarifications or questions regarding the topic, you may send me a message in our group chat. Also, do not forget to answer the following activities: what I have learned and what's more, which are found on page 2 of your Module 5 in Quarter 4 of General Physics 2. After answering the activities, continue reading lessons 2 and 3 in your module. Once you are done with the rest of the lessons in Module 5, you answer the post-test. So, these are all for today. Goodbye everyone, and keep safe always. Thank you for watching.